Hi guys, Harrison here. Um, I hope you guys are having a good day. Today my goal is to talk about convergence of Fourier series. Due to time constraints and lack of knowledge on recording, I will be just talking about convergence within the Hilbert space and voiding completeness and pointwise convergence within this talk today. But to start the talk, I've decided to break the talk into two parts. Part one, where I define helpful tools, and I talk about definitions of things that I think are helpful to have cleared up before we start the proof, to, in the end, help us complete said proof. So our first tool would be a norm. A norm is on a mathematical object like a space or set, the definition of a length, size, or extent. Um, a good sort of example of a norm would be the norm on R1, where I take an element like 5 and an element like -7 and subtract one from the other, take the absolute value of that, and you get a distance or length slash size of 12. And then on Rn, it's that Pythagorean theorem that we all know and love from Calc 3. It can be, you can choose a different norm for different spaces, and multiple spaces, a single space can have multiple norms that are valid. Now the next tool would be a Hilbert space. This is a complex inner product space. What that means is it's a complex vector space where there is an inner product that associates complex numbers to each pair of elements, such that it satisfies three important properties. The first one is conjugate symmetry. This means that the inner product of a pair of elements um, can have those elements inverted and still produce the equivalent answer or inner product. Um, it follows that the inner product of xx is a real number, such that if you're multiplying two complex pieces, you get a real piece, and two real pieces, obviously a real piece. And then that this inner product is linear. We won't really be proving any of these statements. These statements are just following from the definition. Um, their third tool is the Cauchy-Schwarz inequality. And this inequality just states that on an inner product space, like a Hilbert space, you have that the absolute value of an inner product is less, sorry, excuse me, is less than or equal to the norm of an element times the norm of the other element within the inner product. And this equality is true if and only if x and y are linearly dependent, which we can now define the space that we will be working in for our Fourier series proof, and this would be the L2 space. The L2 space is defined as a space that has a norm squared or a square integral norm such that it is defined as on the page. And this space satisfies linearity, which I stated previously. It is also a Hilbert space, so some of these follow from Hilbert space. It satisfies the triangle inequality, which is follows from a vector space, but I did a short proof showing that this norm would apply to the triangle inequality as well. And then the Cauchy-Schwarz principle, such that here x and y are linearly dependent, so that you can have an equivalent sign there. Then we can define our inner product on this space as f of g equaling 1 over 2 pi integral of f of x times g of x dx. All right. Now what I want to do is go back, I think, and define our Fourier constants on this space where C sub k, since the Hilbert space is complex, we are using e to the ikx, but later on the presentation we will be converting to our more formalized notation. This is just to show you that you can have a complex form and it will work for all of the proofs that I will be doing. But the inner product, by definition of Fourier constants, is C equals f, the inner product of f and e to the ikx. If you want to see this, see why this is, you take the definition of the Fourier, um, saying that f equals c to the k, the summation of c to the k times e to the ikx. You take the inner product of both sides. E to the ikx has orthogonality such that it fades out when taken with the inner product of itself, and then you're left with ck equaling f, the inner product of f times e to the kx. Now, aside from the specific example we're going to talk about now, Hilbert spaces are useful in physics and many other places. In physics, we use them to describe the probability underneath the wave function of a probabilistic particle like an electron. And we take the real and complex wave function norms of each and multiply them together such that we have the square integral of the wave function equaling 1, which means the probability of the particle being somewhere on that bound that you chose is 1. It's really interesting. I didn't realize that electrons could technically be in an imaginary space, but it's a weird concept that I would not rather touch today. Pretty interesting though. So now we're going to define convergence, and this is just the definition of convergence that we'll be using today. It is different from pointwise convergence, and that definition or that difference doesn't really affect in finite dimensional vector spaces. However, if we are going to be using infinite dimensional function spaces, like L2, for example, or other Hilbert spaces, we would like to have a definition that works for those spaces. We can show that pointwise does not work for a function like the one in this example, and our definition of convergence that we just defined will. However, due to time and me not wanting to present any false information in case I was wrong, I will leave that as an exercise for the reader. So the last definition I want to tackle is orthogonality, which we have had plenty of experience in. Let V be an infinite dimensional inner product space like our L2 space, and suppose that phi 1, 2, 3, etc., or orthonormal collections of elements in V. These orthonormal collections, orthogonality is defined by the inner product. One of the definitions is that the inner product of these two orthonormal elements are 1 if the element is the same and 0 if the element is different by a factor of j, k, or n, as we will use later. And again, we're just showing here that the orthonormality of psi is what allows us to define each constant of our Fourier series. And then here I state what I stated previously, how now we will be pivoting to just using our orthonormal elements in our L2 space as cosines and sines to be more in line or consistent with our studies that we had previously throughout the semester. And now we're on to part 2. We're going to be proving a single proof within the book. Hopefully I've broken it down into steps that are manageable. The first step we'll do is we will look at how a Fourier series is the best approximation for a function in a least squares sense, and then we will show what families of functions allow our Fourier series to converge. So, what we want to prove for our least squares sense approximation or definition of Fourier series is we want to prove that if we had a v sub n, which is the span of the orthonormal vectors or functions within V, that the nth order Fourier partial sum, S sub n being the summation of orthonormals times constants, is the best least squares approximation for an f that belongs in that same V sub n, meaning that we're minimizing an f minus p among all possible p sub n elements of V sub n. By the end of the proof, we will hopefully have shown or defined p sub n to be s sub n, but for now we are just introducing a new function p sub n that will look very, very similar to our s sub n. Here is our p sub n that we have decided to define with a constant d sub k multiplied by an orthonormal vector psi sub k, which is an element of our v sub n, which is, as we mentioned, our n-dimensional subspace that spans our infinite dimensional vector space. And then from orthogonality properties, we can rewrite p sub n using our definition of inner product as well, or using our definition of the equality of the square integral norm and the inner product to define the norm squared of p sub n to equal the summation of the absolute value of d sub k squared. And then up in the top, I have our formal definition of the Fourier series and the S sub n that it is defined to converge to. And you can see the similarities between our S sub n and P sub n that we chose to start this proof. Now, from equality of the norm and inner product, we can calculate that the inner product, or we can calculate the inner product of, or from the equality of the norm squared and the inner product, we get this relationship, and then we can calculate that inner product of f minus p sub n and f minus p sub n, where f and p are squared, using FOIL, such that we can rewrite those as the norm squareds, and then we collapse our 2 times fp back into an inner product. And then up in the top, we have references of the definition of the inner product and the norm. And you can see how those similarities can collapse, and you can follow along. From our definition of p sub n and its linearity, we then have the substitution where we are substituting. Oh, yes, where we are substituting for that inner product of f and p sub n. We're substituting p sub n for the summation of d sub k times f, or times the orthogonality functions. D sub k being a constant and the linearity of the inner product allows us to pull that out. And then what we'll be doing is showing that this summation of, or the inner product of f and the orthogonality is our definition of our constants from a Fourier series, and from the beginning that the norm squared of p sub n is equivalent to the summation as I've included at the bottom. So we will then be plugging in those two ideas, which change our d sub k times the inner product of f and the orthogonality plus the norm squared of p sub n to these two values. Um, However, we would like to transform these values into something we know plus something else. We can do that by adding a positive ck squared and negative ck squared summed to, within the summation such that it's summed over all ends that I might not have included. Um, Such that we can then use our FOIL again to FOIL these two elements here using or bringing in the 2 and the negative, and then keeping this negative ck squared absolute value here. Then what we will do is we'll say, let's look at our definition of the Fourier series again. And then we're going to take the square integrable or the norm squared of this function and you can show that it equals the constant squared. Having that norm squared takes the inner product of these two orthogonalities, giving you 1 for all the constants, such that that term ones out and disappears. You then get this definition, and then this can be plugged in to here such that we now have our definition of our original function. F minus p sub n is equal to this, where c sub k minus d sub k is a term we can change. When you think about it, f is given to us within this proof. S sub n is given to us within this proof because it is all changes dependent on f. However, the constant d sub k is dependent on the p sub n that we choose at the beginning of the proof, such that similar to an epsilon delta, where you have the devil giving you a term. Here our devil is giving us an f, and we have to choose a d such that this f is mapped well by our Fourier series. We are trying to choose a d such that dk equals ck for all k's, which voids out this third term, and we show that within least square, our Fourier series is the best approximation of f. This is that S sub n is equivalent to P sub n. And if you remember, we said that this is always less than or equal to this, such that they are equal. So this is the best approximation. Now we're going to choose a P sub n on a subspace of our L squared, and try to use the theorem that we just proved to show what the family of functions that our Fourier series can accurately describe or accurately converge to is. So we're going to take the subspace of sines and cosines on this Hilbert space L squared, and we can show that, or we can choose a P sub n right here such that our orthogonalities are cosine of kx and sine of kx, and our constants are r sub k and s sub k. Then from our previous proof, we can set p sub n to s sub n and d sub k to c sub k, where s sub n is the solution to our Fourier series and c sub k is either r sub k or s sub k, or a combination of two. Or either or, and then we can plug both in using linearity. Either way, we can plug these in and see that using simple arithmetic throughout our norms, we can have the solution come to be that our series is bound, our series of our constants squared is bounded. What we can deduct from this is that if the constants are bounded, then the sequence of the constants approaches zero as n approaches infinity for the f in V sub n, or in that subseries, in that subspace that we talked about, such that if f is an element of L2, um, meaning if f is square integrable, then its Fourier coefficients satisfy a sub k, following out this, and b sub k approaching zero, such that our f will converge in our Fourier series. And the Fourier series will accurately describe our f. There is a slight caveat with speed of convergence. There is still some elements outside of this space that can converge for Fourier series that converge very, very slowly. However, this is a majority of the convergible Fourier approximations. Final thoughts. I really enjoyed this idea. Um, I hope I did a good job explaining it to you and that you guys could follow along throughout my steps. And we did not touch this as I mentioned, but within chapter 3.5, you can use completeness on this Hilbert space, and you can do a proof of pointwise convergence for the Fourier series, which is more clever, or also a very clever proof. Thank you guys. Best of luck on your presentations if you watched this first. Um, or if you didn't, I'm still recording this before you did them. So best of luck, guys. Thank you for watching and have a great break.